Hi again. So we're following on from our series of videos about general solutions. If you haven't watched the previous videos, I strongly advise that you watch my video on general solutions for tangent and general solutions for cosine. This video, however, is about the general solutions for our sine function. It's really important that you have a look at cosine and tangent because it helps you get an idea of what we're doing. Sine is a little bit more complicated than cosine and tangent just because we've got variations in the orientation of where we place the angles. So what we're considering here is an equation of the order of, let's say, sine x equals some value, let's call it z. Okay, and if we want to find x being the angle, x is going to be the inverse sine of z. Now, when we talk about sine, we are talking about the vertical inclination of the angle around the unit circle. So if I look at this first equation, okay, in this form, what I'm really saying is that z is going to be some value located on the y-axis, and that's going to correspond to an angle x around the unit circle. So here we can say x equals sine inverse z, which we have previously here. Now, because we're going around the unit circle, what we can do is we can always orientate it around this point here, which can be 0, 2 pi, 4 pi. Could also be negative 2 pi going into the negative realm. And what we can tack on here is plus 2n pi. So that variation means that as we go around the unit circle, so if I go around, let's say one go around all the way to here, again, that's plus 2 pi. I can go around a second revolution, that would be plus 4 pi, and so forth. So we just have to understand why we're adding on that plus 2n pi. The other interesting fact which I want to consider is also that we're going to have another result which is going to be located at this point here. And because of symmetry, and sorry, I'll just neaten that up a little bit. Because of symmetry, we're going back by x. So this can be, and if I think about what this value is, that's pi. So this could be as an example of pi minus sine inverse z, which is x. But what we got here is we have pi here. We could also have here negative pi. We could have 3 pi. And I want us to recognize that we are talking about coefficient. So what value we're putting in front of pi, whether it's 3, 1, or negative 1. That's going to be an odd term. So to get an odd term, we're going to write 2n minus 1, and whatever value of n, remember n's going to be an integer of some value, so it can be positive, negative integer, but it's going to be an integer. That on this region here, that's always going to be a odd term in front of that pi. So the general solutions for our sine functions come in two forms. Okay, so we can say x equals, and I'm just going to write it as 2n pi plus sine inverse z. That's talking about this solution here. And x equals 2n minus 1 pi, not plus, should be minus, sine inverse z. And they're our general solutions. So we have to consider these when we're looking at solving problems. So let's go and have a look at a couple of problems. So first problem, evaluate the general solution for sine x equals a half. So as we have been doing in all of our other videos, we're going to do a quick sketch with a unit circle. So just a very quick sketch. Okay, that will do for there. I'm going to locate a half. It's positive. It's going to be located on our y-axis. That means I've got 2 points there. Okay, but I'm going to focus on this point, and if I know my identity triangles or my exact values, I know that this angle here is going to be pi on 6 or 30 degrees. So therefore, I can say for my general solution, x equals 2n pi plus sine inverse a half, and x equals 2n pi plus pi on 6. Okay, we might want to try to just neaten this up a little bit. So I'm going to say 12n pi plus pi all on 6. And then let's take a factor of pi out of here. So 12n plus 1 on 6. Now that's one solution. That's one solution. We have to focus now on this other side. So I'm going to write and here. And x equals 2n minus 1 pi minus sine inverse a half, and x will equal 2n minus 1 on pi minus pi on 6. Now we might look to neaten this up a little bit. So I might say 6, 2n minus 1 on pi minus pi. Okay, all on 6. And then if I get it to take pi out, and I might expand the bracket. So I have 12n minus 6 minus 1 all on 6. And if I and there's my general solution for the second part. When working with sine, we need to, there's a lot more work because you're working in two separate areas with two separate equations. So you just need to make a note of that. Okay, so let's have a look at our second problem. Evaluate the general solution for root 2 minus 2 sine x equaling 0. So what I'm going to do first of all is I'm just going to rearrange this equation. Look, if I get sine x by itself, this should be root 2 on 2. Okay, that's an identity within our unit circle. So a quick sketch of our unit circle. Okay, root 2 on 2 going to be located on our y-axis. Okay, I know from my exact values that that's going to be equal to pi. So therefore, I'm going to say x equals 2n pi plus sine inverse root 2 on 2. this x equals 2n pi plus pi on 4. Okay, and x will equal 8n pi plus pi all on 4, which I can write as pi 8n plus 1 all on 4. So there's my first general solution. I now need to consider this other side over here. So I'm going to write this as x equals 2n minus 1 pi minus sine inverse root 2 on 2. Now this sine inverse root 2 on 2, I know equals pi on 4. Okay, I might try to put everything over 4 here. So minus pi, and then I'm going to continue to work the function. Take pi out as a factor, expand the bracket. Should be 4 minus 1 all on 4. And there we have our general solution. So one general solution is found here. One general solution is found here. And that's how we're working with it. When we come to evaluate general solutions for something where the angle is a little bit more elaborate, okay, so you have some translations or transformations around or dealing with x coordinates, what we're going to do is we're going to just treat this whole term as an angle. So if I rewrite this, what I'm really looking to do is this equals negative 1 on 2. Then draw my unit circle. Okay, negative 1 on 2 is going to be located here. Okay, remember it's negative. Therefore, I'm going to talk about this value and that value. Now, there's ways that we could consider this. Okay, I would probably go a little bit out of the range of using the set equation here just because of the graphic. I would call this, well, you could call this angle negative pi on 6, and I could call this angle negative 5 pi on 6. I'm still going to treat them as in their different ranges. So remember here, I'm talking about 0, 2 pi, 4 pi. Here I'm talking about pi, 3 pi, 5 pi onwards. So one solution that I'm going to put here is, and I'm going to focus on this solution here on negative pi and 6. So this is going to be 2n pi, because 2n pi talks about this area of the unit circle, okay, minus pi on 6, and just made a little mistake here. Just remember that we are talking about this whole term, so I've got 2x minus pi all there, and I have 2x minus pi, okay, and if that was minus pi on 5 pi and 6, so I could say that that's 5 pi and 6. So remember 2n minus 1 pi, that's focusing on this region, okay, and what I'm going to do is I'm going to add pi on 6 because I'm moving in anti-clockwise direction, which is positive orientation as far as our angles are concerned around the unit circle. So now what I'm going to do is I'm going to try to refine both of these terms. So first thing that I'm going to do here is try to get this all on 6. Bring the 6 up here. Minus pi, and we're going to be adding 6, so that becomes plus 5 pi. And I can say x equals pi 12n plus 5 on 12. And that gives us our one of our solutions, or one of our general solutions, namely this value here. Okay, so let's focus on the other one. This one may be a little bit longer to resolve. Actually, not 12. Let's put 6 here. 6 on 6. Okay. And really what I'm looking to do is expand this out. So this is going to be 12n minus 6 on pi plus pi all on 6. Um, 12n pi minus 6 pi plus pi all on 6. I'm going to do a couple of steps here together. So 12x minus 6 pi, that's just bringing that 6, this 6 up to the other side. And then I've got 12n pi minus 5 pi. 12n pi plus pi, once I bring that across, and then x equals 12n pi plus pi on 12. Rewrite this a little bit further. Take pi out as a factor in the numerator. And there we have our general solutions. So that's one general solution. That's my second general solution. And we can substitute n with any integer, and that will give us a solution around the unit circle. Hope this helps. Have a good day.